Okay, here we are again. It is the video lecture, the psci 168 video lecture 7. And a lot of great stuff today. So I'm going to do some review, and I'll immediately write a couple homework problems on the board in order that we don't save for the end, right? So I don't forget. But let me begin before that with a couple of announcements. So the first thing is I've received a whole bunch of notes now by the time you get this lecture, and we've seen some really excellent notes. So let me just encourage you to keep taking the best notes you possibly can. As I said before, I'm responsible for the logic and the structure. The whole thing's going to unfold, and you just take the best notes you possibly can and leave a lot of space. You know, space for pictures, space for extra comments, and it's going to be great. Now, I took some video lectures out of the queue. What I'm going to do is start taking them out for a couple of days. So the Monday lecture, Wednesday, Friday, the lectures for a given week will be posted one at a time, but then I'll fill in all the subsequent ones again. I just want to make sure that people can get their notes Monday, Wednesday, and Friday and not put it off until later. That's the whole reason. So I'll eventually repopulate the entire playlist so everything is there, okay? But from now on, I'll post a lecture and leave it up for 2 days, and then I'll post the new one and take out the old one. And at the end of the week, I'll put them all back in. That's how it's going to be. Good. So that's that. And the other thing is the homework problems that I'm going to put up here just go in the body of your notes, and you just turn them in with the notes. And in fact, if there are any questions about them, I'll return to the subject and solve them for you so that you can put that in there as well. But you want to give them a good try, leave a lot of space in there so you can return to them as well. Then that way you turn in one set of notes every week, Friday at 6 o'clock. Okay, that seems to work pretty well. I have some other really giant classes, so it adds up, but it's working pretty well. So notes, etc. Notes, videos, homework, etc. Took care of that. So we'll begin with a little bit of review, and then I'll formulate the homework. So review is forces, vectors, structures. We went over this. You guys had a chance to hopefully download all manner of beautiful pictures and understand what it is you're actually looking at now that we've learned about forces and vectors. And the idea with the forces is it's a push or a pull. The idea with the vectors is they add like arrows, and forces are vectors. And I'll give some nice examples, but because they do this, you can just use what you know about triangles. And then we have some interesting structures. So here I'll formulate the homework problems. And see what we have here. So the first thing was, remember we had that demonstration. I had the scale, I had the other scale. In between the two scales, I had 10 newtons. And we're going to think that this is symmetric, but I'll just work with one side of these. Okay. So this is the reading in the scale, and that's the tension in the string. We'll call it capital T question mark. What is it? What is that tension in the string? This is a force. We're going to call it capital T. Well, here's the thing. we know that this arrow here is composed of these two arrows. In fact, let's not use the letter T, we'll use the letter F. Tension F equals question mark. What we do know is that this short vertical side is 5 newtons because it's half of these 10. This hypotenuse is what we're looking for. Well, how can we solve that? We can solve it by knowing the measurements of this triangle. So I'm going to repeat this triangle. Okay. So these are now similar triangles, but I'm going to label these with lengths. So this length here, I'm just going to make up a number, is 0.9 meters. And this length here, let's say, is 0.1, let's say 0.13 meters. Okay, 0.9 meters, 0.13 meters. And now we have similar triangles. And what we can say is, up here, F is to 5 newtons as this unknown length is to 0.13 meters. So you have to find that unknown length. But once you set something up as similar triangles, it's just yours to figure out. So that's the first problem. Go ahead and find F. Find F. Looks like you're going to have to find L first, and then you can find F. Okay, so that's one homework problem. And that was our original demonstration of the vector nature of force. Now the next one is the roof gable version of this problem. So let's draw a little house the way we learned to draw them a long time ago, right? This is how we drew a house, had a door in it. Okay, fine. Now I'm going to stand on the roof, and my weight equals 900 newtons. Now we know that the force is going this way. It's just the inverted version of that one up there, but it's going down and across. And now, for the principle of construction, we're interested in how hard is this thing pushing to the side, because we're going to have to somehow brace it in order that it doesn't tip over outward. So this is the force that we're looking for, and we know that the same thing is happening to the left there. So this side of that triangle is half of my weight. It's 450 newtons. So again, we have to know the dimensions of this triangle, and I'll just repeat this triangle here. So this is the same one. It's labeled 450 and F, and now I'm going to label the lengths 3 meters and 1 meter. 3 meters and 1 meter. Okay, so these are similar triangles, and this time I'm just going to find the unknown F. Find F. Good. Those are little puzzle type of problems, but they're very germane. This is the whole principle of the vector nature of forces. And if you've got those Gothic cathedrals in your list of pictures, then you will have seen that all manner of interesting buttressing was done in order to keep those tall walls from falling outward. Good, so that's a homework problem, and finally I'll add one with the law of the balance. Homework, law of the balance. And with this we can then move smoothly into some new material. So law of the balance, I showed you last time, you have that in your notes. So there's a, let's make this a little more elegant. So we have a uniform beam of some sort here suspended right in the middle. And that's a point, and I'm just going to so these tick marks are equal distances apart. Equal distances, and I'm going to put 9 kilograms here. These are equal distances apart. Question mark, how many kilograms is the unknown right here? So I'm counting over 1, 2, 3 here, and 1, 2, 3, 4, 5 here. Okay. So find the unknown mass. We're using mass and weight interchangeably now because we haven't gotten far enough to really differentiate them. Okay, so we can use the law of the balance of weights, forces, masses. Good, so we have 3 homework problems. Make a nice picture of them, leave plenty of space to solve them, and just they're part of your notes, and they're part of the notes that you will turn in. And I can always come back and solve them for you if you need that. And sure, we can come back and solve them. So that is a good piece of review because we've got the vector nature having to do with structures, we made it to the law of the balance. And now I just want to extend the law of the balance to levers. Now normally in class we would have a fulcrum and a big board, and we would all climb on the board and lift each other and really understand the law of the lever. I'm going to just draw pictures for the law of the lever this time, but they should be convincing enough. And then I have an excellent video that I'm going to recommend. So first I'm just going to discuss the law of the lever and then the center of mass. Okay, so the next topic is the lever. And we're going to begin with a massless lever, or an object that has much less mass than the things we're actually going to move with it. Okay. So we're going to ignore that this is just a bar. And what we do is we place a wedge here. Here's the ground. And this is called the fulcrum. And if I push down on this end, I can push up on this end. Right here, push down here, this thing pushes up. And what we like to do is get a big enough one and actually stand on the end, and then we can lift each other up, okay? And the question is, what is that law? And the law works just the way the balance did. Okay? So if I have more length on this side, I don't need the same force as your weight. So I'm going to, once again, F1 and L1, and then to lift here, I'll have F2 and L2. And the law of the lever is really the same as the law of the balance. We can do many different versions of this. We can lift a person, we could lift a car, Or we could use this with a little thing to pull nails out. So on a smaller scale, we're always using leverage. A lot of hand tools use leverage. But the way I want to introduce this is it's just like the law of the balance. So the law here is that F1L1 is equal to F2L2. And what you can do is just generate a very large force with what we call mechanical advantage. Okay. So how much weight can I lift? So to lift F1, and F1 is just a weight, we're going to solve for F1. That's F2, which is my applied force. I'm pressing down there, and I'm just solving algebraically, so it's L2 divided by L1. So let's put a box around here so we can focus on it. Say I want to lift 1,000 pounds, okay, and I can only press down with 200. Then I need another factor of 5 here, and this L2 over L1 is the mechanical advantage. Okay. So in this case here, I'm just going to measure them off. I've got about 1, 2, 3, 4. Got about 4 times as much on this side as on this side. So I'm going to get 4 times my force. So this is the force that I'm applying on my side. This is the force that's being delivered. Okay. So in my picture, I'll put it back down here. Applied force is on this side. And this is the force that's generated. Okay, so once again. So yeah, make sure you write this out and see what's going on, because it's just the law of the balance. And you can analyze this with triangles and so forth, similar triangles, but it comes from that basic law up there. Now, it gets a little more interesting, and in fact, right now this is a massless lever, okay. Or the lever has negligible mass compared to what's being lifted. So what if the object is itself massive? So for a massive object, for a massive lever, that is to say a heavy lever, it's not going to work exactly the same. If this board weighed as much as I do, then this formula would not work. If the board weighed as much as I do, the formula wouldn't work. But there's an easy way around that, and that is that a uniform object has what's called a center of mass. Let me write that down. For a massive lever, we need to know about the center of mass. And the center of mass is simply the balance point. So this is a 1 meter stick, okay? Best way to look at it. It's a 1 meter stick, and I can balance it right at the midpoint. So the center of mass is at that midpoint, okay? And this thing weighs something. If I put it on the scale, it weighs something. And so the law of the center of mass is that that's exactly where the weight is located. So this stick, you could pretend it's completely massless and that the mass is completely concentrated at that center of mass. Okay. So example, and this picture does everything. I need a little more room. So the example center of mass, first of all, center of mass, that's what this is, COM, is for our purposes, it's the balance point. So we have that ruler, for instance, that I like to carry around, and the center of mass is right where it would balance. And I put a little star there for the center of mass. I like to put a little star. Now this next problem I could even put as a homework. So leave a lot of space in your notes. Actually, this one I think I'll solve. So the example with the center of mass, here I'm going to take, a massive object. This is a beam of some sort, and I'm going to put it on that wedge right there. And as you guys can imagine, if I hang an object from the string, say 100 newtons, I think you can all imagine that here's the situation. This thing, of course, would just fall, but if I hang the appropriate weight from one side, it'll be balanced, okay? And now here's the thing. Even though you can't see the center of mass, for this thing we know it's right there, and just for the, okay. And here we have, I'll call it F sub beam. Okay. So the total weight of the center of mass the total weight of the beam acts at the center of mass. And if you know that, it's just the law of the balance again. So we will have an L1 to that pivot and an L2 to that pivot, and we will have instead of 100 newtons, let's just call this the weight. Weight sub 1, and in fact I'm even going to call it F sub 1. That's the weight, and again it's the law of the balance. So this thing is just alone. There's nothing hanging from this side, it's just suspended under its own weight. And so we have F1 L1 is equal to F sub beam times L2. And this F sub beam, the weight of the beam, acts at its center of mass. Did I write that down? Important note. Weight of an object, the weight of an object acts at its center of mass. Acts at its center of mass. So yeah, carefully put that in your notes, and you could even make up some problems on your own for this. They're just like my law of the balance problem, except the unknown mass, well, one of these is an unknown mass, right? The weight of the beam acts at its center of mass. Good. So this is important for construction, and now I'm going to recommend a really interesting video. Let me see how minutes we are in. A minute, 25 minutes. Good. So we'll send this thing up here. I'm just going to spend the next few minutes describing a video that will be posted to our playlist. And I will call it the Wally Wallington Stonehenge video. So next, is a real person, Wally Wallington. Stonehenge. I think it's about 6 minutes. It's not that long. Doesn't matter. I'm going to post it to our playlist. It's one of the all-time great short videos. So first of all, what is Stonehenge? Stonehenge is an ancient monument over in England, and it's a big set of giant post and lintel structures in a circle. These are enormous, you know, maybe they're 10, 15 feet high, they're stone, and the question, or maybe higher, the question is, how were they built? So there's a construction worker out in Michigan who started using leverage, just what he could do with his own hands, to start building things like this and doing a lot of other interesting stuff. It's one of the best demonstrations of leverage and construction you'll ever see. So I'm going to post this video in our playlist, however many minutes it is. It's not that long. It's really good. And definitely show me some screen captures from that. And you know, if you can't even take some notes from the video, print out some screenshots. You're really going to like this. And what I'll do in the next lecture, I'll actually spend some time discussing, you know, reiterating what he did and the leverage, because to understand what he did, we have to understand this center of mass example and the leverage example that I just had on the board. And what I've seen is the production is so excellent here. The sequence, the systematic explanation of what he's doing is just perfect. It's just perfect. He uses leverage to raise a 19-ton concrete beam up off the ground, and patience, and it's fantastic. Okay, so this video that'll be in our playlist, you want to watch it, print out some screenshots, and then next time we'll discuss this construction principle, and that'll take us right into where we want to go in terms of energy. So it'll be a finish to an end to this, so to speak, this chapter that we've been working on. Forces all the way into structures and construction. So next time, force, work, energy. All right, these are technical terms. We know all about this, and then we'll be on our way. Okay, good. See you all next time.